Hello, everyone, and welcome to differential equations. In this section, uh, I'm going to discuss the background. As you know, some schools, of course, require calculus before uh, this course, and some others require even linear algebra. So it depends. However, calculus is used, and this course is considered an application to calculus. It's very interesting, and you will see a lot of nice work in it, and it is applicable to different areas. So let's talk first about kind of the background. So let's see. In sciences and engineering, of course, you have math models, right? So I'll kind of explain this. Or you will hear mathematical models, and these are the ones that are used to describe or represents physical phenomenon or um, physical events or situations. And I'll give you some examples of that. And that yields two derivatives. So, or let's just say derivative of a known function. Derivative of a known function. Because that's the important part that we need to understand kind of at the beginning is this equation that you're going to deal with in whatever application it is and involves this derivative of a known function is going to be called a differential equation. And often I will just do these DE for it, right? So an example that you've seen, and this actually starts early in algebra, let's say an object falling, right? And or a free fall. And if an object is released and we have a height, let's call it h, then there is a force. This, of course, is going to involves Newton's law or Newton's second law. And as you know, the equation that you've seen before, and it was done in different ways, we're going kind of give a review to it here, is there is a force that is acting on this object. And of course, we're just going to say the gravity. And we're going here to eliminate or kind of dismiss or ignore other forces or are not used, or they are too small to be considered. Of course, like resistance due to friction or something. So if this object here has a mass m, then we have the mass times the acceleration is going to equal to a total force acting on it, right, on this object. So the mass is m. The acceleration, remember from calculus, is that second derivative to a position. And the gravity here is going to be that force negative because of the direction mg. So that's the Newton's second law. And we take this and we try to figure out, let's say, the position, which means you need to integrate. So we're going to go from the second derivative to the first one using integration. Then you're going to get y, because we need to solve for h, right? Solve for h. Let's rewrite. Um, of course, m here is constant. And often I would write this for constant. So we can divide by m. It's not 0. We can do that. Then we get dh dt is negative g. This is still the second derivative, right? Then integrate to go to this first derivative, and that's going to give us negative gt plus the constant of derivation, constant of integration. Okay. Then we'll integrate again. That takes us to h, which is in terms of t. And here, this is 1, so we'll do 1 plus 1, which is 2. Then divide by 2 to make up for it, right? Negative 1/2 gt squared plus this c1 is going to be t, and the new constant of integration. And now you can see this equation that you've seen even from algebra, all the way from algebra. And these constants here are going to be decided by some initial values. Let's say they're going to be decided by initial values, and we will see these in the examples. So for example, initial position, initial velocity, and all that will give you these. So next thing is, let's talk about radioactive, an example. So the first example here I gave you is this one. We can call it example 1. Second example here, some radioactive decay. And you've seen even, again, in algebra, decay and growth with exponential and the rates and all that. Then you've done it, of course, in calculus. So let's put here the rate of decay. In calculus, we do dA dt, negative k, the constant there, which has to be positive. And A is going to be the amount of radioactive substance. This is going to be the amount of this radioactive substance. So the ADT is the rate in which it decays with time. And of course here, a nice thing to show, as we need this going into the course. To integrate, what I will do first is I will kind of separate them because you see dA by dt and these differentials. Can we separate this? Can we put dA and divide by a? But multiply both sides by dt. So what happens, right? Because I think in the beginning of calculus, you look at these differentials but you deal with them as if they always go together, but you've seen somewhere where you can separate them. So doing that will give you a nice thing here. So when you integrate, you can this by it has the a and this has the t. So we have here 1 over a. Remember for antiderivative there for 1 over a is a natural log. Of course, the amount is positive, so we don't need the absolute value. We usually use the absolute value if we're not sure. So natural log of a plus the constant of integration, and here minus kt plus some constant of integration as well. And somewhere as well in calc, you solved, or calculus, you solved this type of equations. So we need to solve natural log of a plus c1 equal negative kt plus c2. So pause the video and ask, what would you do in this case? How would you open all this up so we can get the a, right? And the constant are just constants. All right, so we know if we take the natural log to both sides, that will lead to something, because we have, if we take exponential or e to both sides, that lead to something because you have natural log here. So let's do that. So e natural log of a plus c1 equal e to negative k t plus c2. We know if you have exponents, they're added, that means they came from multiplication. So we can change this to e to natural log of a times e to natural log of c1. Of course, x2 times x3 is x2 plus 3 here. So that's kind of the idea. So we'll do the same thing here. These kind of inverses of each other, so you'll get 1, which is here, times a, and e to c1, we can still leave it there, it's a constant. And this is remains as e to kt, and e to c2 is just another constant. So because I'm interested in a, what I will do is I will divide by this constant, and I will get e to negative kt here times ec2 divided by ec1. So this is all some constant. All right. And that gives us, in terms of t, e to negative kt times that constant, let's call it, of course, if you want to do one more step, you can do e to c2 minus c1. That's constant. So we can replace this whatever constant with just another c, another something constant, right? Of course, c now has to do with the c1 and c2, but they're all constants. So you've seen this formula in a lot of different places. We saw it in algebra and pre-calculus, and of course calculus. And c is a constant, and it's how can you determine this? It's a constant. It's also determined by initial amount. Of course, when t equals 0, this e to negative kt becomes 1, and that gives you the initial amount. So c goes with the initial amount. So although both examples are simple here, and they do give us a good understanding to where we are going, and you see the benefit of calculus showing up. These examples give us insight into the study of differential equations. The solution here of a function, as you realize, it's not a number, it's a function. So that's the most important thing to understand what this course is about. Before you're trying to solve something and you find a number, but here we're trying to find a function. All right. And of course, we use integration, we use antiderivatives, and we have constants of integration, and we're going to need to use some initial ideas and information to find these constants, right? And if you look at the book and you look at the notes, there are a lot of examples. I can tell you more, especially if you want to Google them or look online. There is differential equations used in banking, electric circuits, of course, psychology. That's also very interesting. When you go to social sciences and psychology and you start to model behaviors, you can also use here differential equations. And let's show you that example before I close this one here. So so for example, here is a rate dy dt, and y 3/2 1 minus y 3/2 equal to p over n. So this is kind of a learner skill level per time, and we have p and n here depend on individual learner or the person and the nature of the task. So you can look more into this. And of course, for engineering, you have vibration. Let's give that one. It is second derivative. Minus c square second derivative respect to position, and here with respect to time. So this is T, of course, represents time, and X it represents location, and C is the wave speed, and U is the displacement of the string that is vibrating. U is the displacement of that string, and as you see here, which is a function of time and location. And of course, these are interesting, and you'll see a lot more of examples, but this is, of course, just the background and the introduction. Thank you.